Hello. Today we are going to discuss approximation methods. The approximation methods in quantum mechanics are very important. By using these approximation methods, we can calculate exact values of Hamiltonian. And those are the real existing problems. Most problems in quantum mechanics cannot be solved exactly. The exact solution of the Schrodinger wave equation exist only for a few idealized systems. In general, the potential energy of most of real systems are different from those we are considering in the case of idealized systems. So the exact solution is not possible to solve general problems. Uh, One of the most important approximation methods are three type of approximation methods are there. So the first one is perturbation theory. Second one, variational method. Third one, WKB. So today class, I'm going to discuss with only perturbation theory. After that, we will discuss variation method and WKB method. Okay. So here we are going to study the approximation method for only, stationary states. Variational method. Third method is WKB. So one important note here, we are going to study approximation methods stationary states only. Okay, this is key fact. We are not going to discuss other states. We are only discuss with stationary state, some energy only. Okay. So the perturbation theory is completely based on the assumptions that the problem we wish to solve is in the same sense. Uh, the given Hamiltonian is slightly different from the exact Hamiltonian of the system. In the case of where the deviation between the two problems is very small, uh, perturbation theory is suitable for calculating. The contribution associated with this deviation and the contribution is added as a correction to the energy and wave function of the exactly soluble for the Hamiltonian. So the perturbation theory is basically built on the known exact solution to obtain approximation solution. The basic idea of perturbation theory is taken from the classical mechanics by Schrodinger perturbation. Schrodinger perturbation theory is now classified into two kinds. One is a time independent perturbation theory. Another one is time dependent perturbation theory. So each of these is useful for the specific problems First, we are going to discuss time-independent perturbation theory. So this method is basically this time-independent theory, the most suitable when Hamiltonian, is very close to the a Hamiltonian H naught. That can be solved exactly. In this case, here we are going to split the Hamiltonian. We know actually Hamiltonian, this is general Hamiltonian, right? Hamiltonian H is equal to kinetic energy plus potential energy. This is general Hamiltonian of the system, right? So especially in approximation methods, the Hamiltonian H can be split into two terms. This H is split into the two terms. Very, very important. One is H naught, and the one is H suffix P. Okay. Where H naught is unperturbed Hamiltonian of the system. So you always remember this. H naught is of the system, and HP is perturbed Hamiltonian. So here HP perturbed Hamiltonian is very small. Perturbed Hamiltonian is very, very small compared to, not using any mathematical letter here. Okay. Very small compared to H naught. Okay. So that means, for sake of convenience, I'm going to write H suffix P less than H naught. So this is the deviation. By using the Schrodinger one-dimensional, two-dimensional, three-dimensional problems, we can't solve this type of deviation. Is, for example, let us say two electron system. If you take hydrogen atom, one nucleus is there, one electron. Okay. So if you take the two electron system, this is one electron, right? So if you take the two electron system, okay, uh, here maybe here another electron is there. This is first orbit. In case if you consider the second orbit. So normally what happened in case if you try to solve this problem of Hamiltonian, so we're going to write this Hamiltonian energy H is equal to kinetic energy of the system, the P square divided by Vm plus potential energy. The force existing between the positive and negative potential energy term will come here, right? So whereas come to the, in case the system having the two electrons, this E1, sake of content, this is E1 electron, this is electron. And generally, in ideal system, we are considering electron 2 and nucleus interaction, electron 1 and nucleus interaction. We are not considering the between the electron-electron interaction in general ideal system solution. But here, we are going to consider the small deviation. So by adding these all small deviation values, then we can get the correct energy level of this. That is exactly what will happen in the approximation method. Okay, so this is the general information. Yes, if you try to understand this perturbation, and perturbation theory. Okay, so if the deviation is very, very small, then we can say right. So now welcome to the how this deviation are formed. In case so one system is there, one atom. In case if I try to place an electric field or magnetic field, the energy levels are going to be split. Okay, there is some deviation. So the type of deviation we can call it here the perturbation. We can expect perturbation when the system is subjected to small electric or magnetic field. We can write this perturbation term. We consider the situation Hp equal to lambda into H prime. So this will happen only. So this will happen only. Uh, so system is subjected to small electric or magnetic field. Okay. So we know Gemin effect or Stark effect, right? So if you place any magnetic field, so the energy levels are split into the a different type of energy level depends upon the pin value of the system. It will split. So in that case, we are considering the energy level of Hamiltonian, the perturbed Hamiltonian, and the deviation energy lambda h prime. So here the lambda is dimensionless real parameter, the lambda, which is very small compared to the one. Lambda is very small compared to the. So here we got new Hamiltonian of this Hamiltonian H initially we defined H naught plus HP. So in case any perturbation is happened, so this is the deviation. Like I said here initially. So this type of electron-electron interaction, we are not considering initial stages. Here, when we solve approximation, this small energy also, this small energy, we are going to calculate. Okay. So this new Hamiltonian H equal to H naught plus lambda H prime. Now this is the new Hamiltonian of this system. From eigenvalue problem, we know eigenvalue equation. So this is H is operator. That function, this is the wave function. When an operator is applying on wave function, it is reproduced by same wave function and multiplied by some constant. This type of equation we known as eigenvalue equation. Here En is the eigenvalue. En is the eigenfunction. So the deviation energy, if you try to substitute this H value here, the H naught, okay, H naught, observe carefully here, H naught plus lambda H prime. So this is new operator. Wave function psi n equal to the En wave function psi n depends on this H naught, depends on this H naught. It is further divided into two types. One is non-degenerate perturbation theory. Second is degenerate perturbation theory. Okay. So what is meant by degeneracy or degenerate? So I can say this one general example by use. So we know px and py, pz orbital, p orbital, right? So here the state p, p, p. Energy values of the systems here are the same. Those are the p orbital, p orbital. But eigenfunction of the system are different. This is px eigenfunction, this is py eigenfunction, this is pz eigenfunction, which means energy is the same state p orbital. Okay, the wave function is different here. Wave function is one is there, another one is py is there, another pz. Wave functions are different. This type of energy systems we're going to call degeneracy energy. In case if you try to understand Schrodinger one-dimensional, three-dimensional potential box where E equal to, oh sorry, I can write it later. Okay, I square h cross square divided by 2m a square. Here a is the length of the box, right? So into n square x, n square y, n square z. So this is the cubic box, three-dimensional box, eigenvalues of the system. So in case if you try to put here the mean first state one, one, one state, so which means nx equal to 1, ny equal to 1, nz is equal to 1. Then we can get here the 3 equal to n equal to 3 pi square h cross square divided by 2m a square. So this is non-degeneracy degenerate states. So in case same other state is 1, 1, 1. Okay, we can write this 1, 1, 1 here. Here 1, 2, 1, 1, 1, 2. Okay. So these are the three possibilities of next state. So in case if you try to use this is nx, ny, nz, 4, 5, 6, right? E equal to 2 square 4, okay, plus 1, 5, 1, 6. Okay, 6, 5 square, h cross square divided by 2m a square. So this is threefold degeneracy. Threefold degeneracy. So this is the simple way to remember the degeneracy. So non-degeneracy system. Now I'm coming to the definition. The systems have same energy levels and different type of eigenfunctions. That type of systems we're going to call degeneracy. The systems having the one eigenfunction and one eigenvalue of the system, then we can call that system non-degeneracy state. Okay. So first we are going to discuss non-degenerate perturbation theory. Non-degeneracy perturbation theory. In the case of H naught has no degenerate eigenvalues, that is for every energy at En of 0, there corresponding only one eigenstate, that is psi n, like I discussed here. So if you have the one energy value, there exists only corresponding only one state, only one state. This type of systems were called degeneracy systems. So in that case, we're going to write the Hamiltonian of the system, Hamiltonian naught, H naught into, I mean, get function. If you apply H naught, H naught on get function, get wave function, then you can get, I mean eigenvalue equation, same wave function multiplied by some constant value. So be careful here. Here I am using some notations are different. Okay, this n represented this n state of the system. Here the not, it represented the uh, no degeneracy eigenvalue. Okay, so in general, the Hamiltonian H we can apply on this wave function, then we can get a En wave function set. This is general equation. This is general equation. So in case if you try to put this H place, replace our new Hamiltonian of the system, H plus lambda H prime into the wave function equal to En, the wave function set. This is equation number 1. The main idea of perturbation theory consists of assuming that the perturbation eigenvalues and eigenstates can both be expanded in terms of power series, like a parameter lambda is there. So going to extend this E0 like this, En power 0, first one, I mean ground state energy, En power 1 plus lambda square En power 2 plus and so on. This is equation number 2. In the same way, wave function also I'm going to expand in terms of power series. Psi n power 0 plus psi n power 1 plus lambda square psi n power 2 plus and so on. Where terms independent of lambda are known as the two terms are there here. Terms of energy in power 0 is this. So this is 0th order. Okay, unperturbed 1. This is 0th order energy. This is 0th order wave function. These are the unperturbed energy, unperturbed eigen function. So here there is no need to calculate this amount of energy. We can proceed there as for the given problem. In case if they are giving any perturbed terms, then we are going to calculate this excess amount of energy. Then we are going to try to add this. Like I said, this two-dimension, I mean two electron problem. The electron interaction also there, right? That type of system. This En1, we can call this energy first order energy term. This is second order energy term. First order wave function, second order wave function. So basically what we are going to do in this approximation method, we're going to try to solve this first order correction, second order correction. So this first order wave function, second order wave, and we're going to add this one thing. Then we can get correct exact solution of the system. So now I'm going to substitute equation number 2 and 3 in equation number 1. In equation number 1. How I am going to substitute in equation number 2. In case if you try to extend this one in terms of power series, this wave function, this energy, and this wave function also. In place of En, this is not E not En. Okay, sorry, this is En. In place of En, we're going to use this term here. In place of psi n, we're going to use this. So please try to remember these three steps, basic steps. Okay, these are the three basic steps. H naught plus lambda H prime. Okay. So in place of psi n, ket psi n, here we are extending in terms of power series, right? Okay. Here I'm going to try to write this power series psi n power 0 plus lambda psi n power 1 plus lambda square psi n power, not power 2, this is second order term, just indicate, okay? It's not psi square, equal to, so in place of en, I'm going to write this en 0 plus lambda en power 1 plus lambda square en power 2 plus and so on into wave function psi n of 0 plus lambda psi n 1 plus lambda square psi n power 2 plus and so on. So if we try to multiply h naught into all these terms and lambda prime into all these terms, then we can get this. So I'm going to multiply these things and we can get this term. Okay, h naught, I'm going to multiply all these terms. H naught psi n power 0 plus h naught lambda psi n power 1 plus h naught lambda square psi n power 2 plus and so on. H naught term is enough. 0th order, first order, second order. So I want up to second order, only I'm considering. I'm not going to third order, fourth order. Those are very difficult. Maybe most problem they're not considering third order, fourth order. Most of the cases they're asking only first order, second order, or ground state. Okay, we try to focus on the ground state. I mean unperturbed term, first order term, second order term. Similar case in the energy terms. Plus lambda h prime psi n of 0 plus lambda square h prime psi n of 1. So here also I'm going to consider the up to en power 0 into the second order term. Okay, so en power 0 psi n power 0 plus en power 0 lambda psi n power 1 plus en power 0 lambda square psi n power 2. Okay, plus and so on, plus, and this term into up to maybe this is 1, 2. Okay, lambda en power 1 psi n power 0 plus lambda square en power 1 psi n power 1 plus and so on, plus this is already second order term, right? Enough. Lambda square en power 2 psi n power 0 plus and so. So here I'm going to find this lambda not term, lambda power 1 terms, lambda power square terms. I'm going to compare these three terms, okay? LHS side and RHS side. The first one, we try to compare. So here only find this one and this one, lambda power 0. Remaining all the terms lambda is 0. So therefore, first equation h naught psi n power 0 equal to n power 0 psi n power 0. This equation number 4. Equation number 4 is one. Next, we try to compare lambda power 1 term. Lambda this term. Here lambda power 1 term is there. Here lambda power 1. Here is 1 term. Lambda power 1 term. Okay. And here also there lambda power 1 term. Okay, lambda power 1 term. I'm going to compare both sides. H prime n power 0 plus h naught n power 1 equal to n power 1 n power 0 plus n power 0 n power 1. This is equation number 5. And remaining term lambda square, second order terms lambda. So two terms are there here. 1, 2, 3 terms are there. Okay. Don't go to up to fourth order and third order. Okay. Most of the cases very difficult to solve second order perturbation also. So we are going to restrict the perturbation up to maximum case second order. N power 1 plus h naught n power 2 n power 2 n power 0 n power 1 n power 1 plus n power 0 n power 2. This is equation number 6. Now we are going to calculate each and every perturbation. First order correction to the energy, first order correction to the wave function, second order correction to the second order correction to the wave function. Okay, first I'm going to discuss first order correction. First order correction to the energy. Once you know how to get this equation, then you can remember easily. Without solving this equation, you can't remember during the national exam. You try to keep on practice this equation. So here equation number 5 is this. Here three equations are there. Here this is zeroth order. There is no need, there is no correction here. Okay, zeroth order. You can solve directly this problem. This is the first order correction energy. This is the second order correction energy. Okay, so in case you want to correct the first order connect, you can take this equation number. So I'm going to explain this thing, the derivation, step by step, how to get this equation. So multiply this equation number 5, equation number 5, okay, from the left side, by draw vector. Okay, be careful. Don't change these operators in whatever we write. So these are the operators, right? In case if you change the position of this operator, sign will. Okay, be careful here. So especially when operator is there, here this is Hamiltonian operator. So this is energy scalar. In case if you change the scalar value here to here, there is no change here. So here is important. Okay. So during the while multiplying this vector here, don't change these Hamiltonian values. Okay. I'm going to multiply this raw vector from the left side of equation. This is get vector, right? This is get vector, this is get vector, this is get vector. Okay. So I'm going to multiply raw vector, equation number 5, psi n power 0, h prime, psi n power 0, plus psi n power 0 h naught psi n power 1 equal to, this is scalar, we can write out of the Dirac notation, right? Psi n power 0, it's better to call this one Dirac inner product, plus psi n power 0 psi n power 0 into psi n power 1. So we know if you apply the Hamiltonian on this wave function, on this wave function, on this wave function. So what you will get here? What you will get here? H naught is there. In case, okay, equation number 4. See here, H naught is applying on this ket ket vector. Then we can get the same ket and multiply with some constant. You can replace now en power 0 psi n power 0. Okay. So I'm going to apply the same rule here. So if I apply here this equation, then I can get E naught, I mean E nth state, so zeroth order into the wave function. Wave function is the first order. Please careful here. And as it is the first term, I'm not changing the first term anything. So it is not possible to change. Okay. That equal to En power 1 psi n. So this is 1, right? Psi star psi is equal to 1. No need to write this stuff. Okay. So this is already 1 plus En power 0 psi n power 0 psi n power 1. These two terms are cancelled, right? So because we can write this is scalar function, this function we can write here. So En power 0 psi n power 0 psi n power 1. These two terms are similar, right? So in case if you want clarity, then I can write this term like this. Or this term we can write En power 0. This is ket 0th order wave function. This ket first order wave function. So these two terms are similar, right? We can cancel these two. So here we can get this answer, right? En power 1. En power 1 En power 1 equal to, so this is the first order correction to the energy psi n power 0. Very, very important equation. Here the H prime is the perturbed term, deviation energy. Now we are going to calculate this deviation energy, first order energy. Then we are going to try to add this first order correction energy term into the unperturbed energy term. Here is there here. See here. First order energy we are going to calculate, then and add this first order energy term into the zeroth order energy term. Then we can get the correct exact solution. Okay, not 100 to 100% solution. We can get don't want to give any numbers, but maybe 70 to 80% maybe correct values of we can get. Okay, so I'm not expecting 70 to 80. So there is some close answer we will get. So this is the first order correction to the. So next class we are going to discuss the first order correction to the wave function, second order correction to the energy, and second order correction to the wave function.